In this video, I just want to remind you guys what a biconditional is. Remember, a biconditional is an if and only if. So it means P if and only if Q. And remember, that's the same thing as P implies Q and Q implies P. So when you see a statement that has if and only if, or maybe you'll see if with two F's, or you'll see the phrase exactly when, they all mean if and only if. And so, the way to deal with these, that's the key word you're looking for. There's nothing particularly new that we're going to learn here, except to remind you guys that this means that there's two things you need to show. There's two expressions. We need to show that P implies Q, and we need to show Q implies P. So this is the same thing as saying, let me do this in black, if n is odd, then n squared is odd, and that is, if that's our P, here's our Q, this is our P implies Q, and we need to prove the other thing. If n squared is odd, then n is odd. So, this is Q implies P. There's our Q. There's our P. So we have two conditionals we have to prove here. So there is indeed two results we have to prove. We have to prove the first one, if n is odd, then n squared is odd, and we have to prove the second one. If n squared is odd, then n is odd. So pause the video now and try this. Remember, when you see an if and only if, means there's two different things you have to do. Okay, now that you're back, we've seen the first part, the P implies Q part. We've seen that before. In fact, we've seen it a couple of times, but this is an example from topic 11. Really topic 10. It's topic 10 when we did some direct proofs. There's an example that is literally this example. So we've done that before. We've also done it in topic 11 when we had a statement that was if n squared is even, then n is even. And we proved the contrapositive of that. So really, we only have this one here. If n squared is odd, then n is odd. And just to be clear, let's say that n is indeed an integer. When I write n is odd or n is even, kind of imbued in that, I'm not being particularly precise, but imbued in that, if we're talking about odd and even, we're talking about integers for sure. If we're talking about real numbers or fractions, odd and even kind of doesn't come into play as much. So when you see words like odd or even, just assume that we're in something like the integers or the counting numbers or the whole numbers, whatever. Okay, so let's do the other part. Q implies P. And we're going to prove this via the contrapositive. We're going to assume the then part is false, show that the if part must be false. So we're going to do this argument here. So assume that n is not odd, so it's even. So that means that n is 2 times some integer k. So I'll tell you that k is indeed an integer. All right, and we want to show that n squared is indeed 2 times some integer. All right, so we have this fact that n equals 2k, so we can start with that. So since n equals 2k, what we can do is we can, of course, just square both sides. We want to show that n squared equals 2 times some integer squared. So to get that squared there, it's probably a good idea to square both sides. So we get n squared equals 2k all squared, which is 4k squared. 2k times 2k is 4k squared. And we want to arrange that in the form of 2 times some integer. So I'll pull out a factor of 2. And what's left is 2k squared. And since 2k squared is indeed an integer, we have that n squared is even. And in fact, I really should tell you here, because it's always a good idea when you're not using a direct proof, tell people what you're doing. This is contraposition. So, there we go. There is our biconditional. We proved both directions. If P then Q, and if Q then P. P then Q we've done in a previous video. Q then P is very similar. In fact, one would say easier. And that's all I want to talk about for biconditionals right now. Again, there's nothing too new there. Just remember that if you have a biconditional, there are 2 different proofs you need to do. Let's move on to the next topic, topic 14, which is proof by cases. So sometimes when you're proving something, it just makes sense, or it makes the argument easier, if you break up your domain into cases that are exhaustive, where you're covering all necessary elements. So let's look at this. So example 14.1 says we want to show that if we have 2 integers, we want to show that a and b have the same parity. So that is, they're both even or both odd. That's what parity means, by the way. If you see the word parity, it means that 2 things share the property of both being even or both being odd. So we want to show that a and b have the same parity if and only if the sum of these guys is even. Okay, so let's try this example. So again, this is an if and only if. Hopefully you've noticed those words. So that means we're going to have to do 2 arguments. So let's do the first direction. P implies Q. So we want to assume that A and B have the same parity. And there's 2 ways for that to happen, of course. The 2 ways are A and B are even and A and B are odd. And that covers all of our cases where the if part is true. So let's assume that A and B have the same parity. So let's do our first case. Let's prove it for the first case. Case 1 is A and B are even. So what does that mean? It means that, well, A is 2 times some integer k, and B is 2 times some potentially different integer L. And again, I'm introducing the symbols k and L. Better tell you what they mean. They are integers. And I'm not going to write the to show for this one, but we do want to show that the sum is even. So now let's consider A plus B. We want to show that that is even, so it equals 2 times some integer. So let's fill in A. We know A equals 2k. We know B equals 2L. And we want this of the form 2 times some integer. So let's just factor out that 2 from both terms here. So we get k plus L. So here we go. We've done it. We've taken A and B, and we've written it as 2 times some integer. So, as usual, we say, since k plus L is indeed an integer, we have that the sum A plus B is even. So that's the first case. Let's do the second case, case 1. Case 2, same idea, is that A and B are odd. And these two cases cover all possibilities where the if part is satisfied. Either they're both even or they're both odd. We're not missing out any cases. That's very important. Okay, so what does that mean? So it means that A is 2k plus 1. Remember, that's how to write an odd number. And B is 2L plus 1 for some k and L that are integers. Okay, so that's assuming our if part is true. Let's show that the then part is true. So we want to show that A plus B can be written as 2 times some integer. So let's consider A plus B. Well, that's 2k plus 1 plus 2L plus 1. Combine our like terms. We get 2k plus 2L plus 2. Again, we know we want to write this as 2 times something. So luckily, all of these terms have a factor of 2. Factor it out, you're left with k plus L plus 1. And then, as usual, since k plus L plus 1 is indeed an integer, we took 3 integers, k, L, and 1, added them together, we get another integer. We know that A plus B is even. There we go. That is the first direction. The first direction broke up into 2 cases. So let's scroll down to give myself a little more room. I'll keep this here for now. Okay. Let's do the other direction. Q implies P. So here, there's a couple of ways of going about this probably. But I'm thinking, if I was to prove this directly, I would assume that Q is true. So assume that A plus B is even. And I'd have to show kind of 2 things. That A is even and B is even. Or A is odd and B is odd. And if I think about that, and you could try that somehow, but it's kind of hard to get a handle on what A and B are separately if you just have A plus B written as an even number. So maybe a direct proof isn't the best way to go for the other direction. I would do a contrapositive proof because, well, here we have, if A and B do not have the same parity, that means they have a different parity. So one is even and one is odd. And we'd have to show that A plus B isn't even, so A plus B is odd. So that might be a little bit better. So let's prove this by the contrapositive. So by contrapositive. So remember, we're going to assume that the then part is false, which is P. So remember here, this bit is Q, or is P, sorry, and this bit is Q. So we want to prove the backwards direction. Q implies P. So that means if we're doing the contrapositive, we assume P is false, show that Q must be false. So let's assume that A and B, well, if P is false, if they don't have the same parity, we'll say that. Assume that A and B do not have the same parity. And what does that mean? Well, if they don't have the same parity, it means that one is odd and one is even. Now, if you think about this, you think, well, maybe let's do two cases. The first one where A is odd and B is even, and the second one where A is even and B is odd. But if you think about that, there's kind of no difference between these two numbers. I'm just saying, pick two numbers that have different parity and show that the sum of them is odd. So it kind of doesn't matter which way around these go. The argument will be the exact same. And if you can see that, you can just do it one way and just say without loss of generality. So we're going to use that phrase here. So without loss of generality, less A be odd and B be even. So again, it doesn't really matter out of A and B which one is odd and even, because that's not going to affect the sum here. Okay, so what does that mean? Well, that means, of course, thus A is odd, so that's 2k plus 1, and B is 2 times L, since it's even, for some integers k and L. Excellent stuff. So there is our P false. Remember, we're doing the contrapositive. So P false, we need to show that Q is false. Okay? So we want to show that A plus B is not even, that it's odd. So let's go ahead. So consider A plus B, which is 2k plus 1, that's our A, plus 2L, that's our B. And the brackets there are just so any reader looking at this will kind of get the clue that this whole bit goes with A, this whole bit goes with B. And, well, we want to write this, remember, an odd number can be written as 2 times some integer plus 1. And really all we need to do is we need to factor out a 2 from the 2k and the 2l, and we'll be left with k plus l. And then we have this 1 left over. That's great. We don't really have to do anything with that. So in some sense, we're done. We just need to write why we know the number is odd. So since that k plus l term, or factor, k plus l factor, is indeed an integer, we know that A plus B is odd. And now we finished our proof. We did both directions. So we're good to go. As a quick summary, of course, well, we have to prove if and only if, so we have to do both directions. The first direction said the numbers have the same parity, so that means that they're either both even, so we proved it when they were both even, or they're both odd, and we proved it when they were both odd. Just two little proofs there. Since it's an if and only if, we have to do the other direction as well. And for this one, it made more sense to do the contrapositive. Again, you could try doing it directly. I think it'd be quite hard. But the contrapositive in this case seems a lot better. So we assume that they have different parity, and we show that the sum is not even, that it's odd. So if they have different parity, well, one's odd, one's even. And since nothing will change if we kind of swap where B and A are here, the argument's going to be the same. So we could just say, without loss of generality, we'll say A is the odd one and B is the even one. The argument would be the exact same if these roles were reversed. And we just do a quick little proof of that. We proved it, we're done. So the if and only if statement has been